Hello everyone, my name is Svetlana Nikitina and today I'm going to introduce you a blast furnace for steelmaking. A blast furnace is used to chemically reduce and physically convert iron oxides into liquid iron. The blast furnace is made of pellet plant, which has 4 process steps: receipt of raw materials, pretreatment, boiling, induration, and cooling. Then we have sinter plant process, coke oven, blast furnace process, basic oxygen steelmaking, and continuous casting. The equipment can be divided into 2 groups: main components and auxiliary equipment. Blast furnace main components are throat, which is the opening on the top; shaft, which is lined with shaman brick and silicon carbide brick; belly, it has straight cylinder shape lined with shaman brick and silicon carbide brick; bush, which is located under the belly, lined with thick layer of shaman brick and silicon carbide brick; hearth, which is situated at the bottom of the furnace, consists of molten iron with a layer of slag on top. It's lined with a thick layer of carbon brick. Blast furnace main components are bustle pipe, which provides the tires with hot air; tire, which is used to inject the hot blast into the furnace from the hot straws through the hot blast main and bustle pipes; tap hole, the molten iron is trapped through the tap hole, allowing liquid iron and slag to flow down through a skimmer opening separating the iron and slag; slab tap hole or cinder notch, which are closed with a refractory clay plug. It is drilled through, allowing the slag to flow into the cast house or cinder notch. A tire is a water-cooled copper conical pipe. It blows hot air into the blast furnace. The tires are positioned around the furnace, and there are up to 12 on the small and up to 42 on the large blast furnace. There are 2 types of charging systems. The first one is double bell system, in which the raw materials are charged into the blast furnace through 2 conical bells. These bells are sealed in gases and distribute the raw materials around the furnace throat. The second one is a bell-less top system. It uses 2 or 3 airlock types hoppers. These are used to discharge raw materials onto a rotating shaft which can change angles, allowing more flexibility. The auxiliary elements are bell conveyors, hoppers, PCI, pulverized coal injection, blower for feeding the blast, hot stove for heating the blast furnace top pressure recovery turbine, equipment for dust removal and recovery. In case of bell-type equipment, the raw materials enter into the furnace through the gap. The bell closes and the larger bell opens to allow the material to fall into the shaft below. In case of bell-less charging equipment, the raw materials are dripped into the furnace through a rotation shaft. Auxiliary equipment are slag car, it collects the slag for disposal; hot blast main, through it the heated air from the hot stove is led back to the furnace; gas cleaner, which removes dust from exhaust gases before burning them in the hot stove combustion chamber; downcomer, the hot blast furnace gas with large amount of fine particles is lit via the camber to remove this dust; cold main blast, in which large volumes of air flow through the cool blast main up to stoves. This cold blast enters the heated stove and heat stored is transferred to the cold blast. Torpedo cars, hot metal is conveyed into this to be transported to the steelmaking plant. Then we have hopper charging conveyor. The raw materials may be stored into stock house, then the furnace burden is prepared, and finally there is a hot stove. This is used to preheat the air blown into the blast furnace. For hot stoves, we have on-gas mode. The stove is heated up by burning gas and combustion air. The heat is allowed to be absorbed into brickwork or checkerwork. Then the sufficient heat has been absorbed. The stove is put on blast. In this way, the cold blast air is forced through the stove and absorbs the heat to become hot blast. The hot blast is then mixed with cold blast to bring it to the right temperature. Finally, it's forced into the blast furnace through the tires. PCI equipment for pulverizing the coal and heating the under pressure, gas inlet, grinding mills, coal storage from coal field, transport air, pulverized coal inner and bin, cyclone, dust filters, clean air, distributor, and blast furnace. Let's talk about blast furnace process. The iron is molten inside the blast furnace. It works by blasting hot air up through the furnace while fuels, limestone, and ore move continuously through the top of the furnace. The hot blast reacts with the coke and pulverized coal in the belly and bottom of the blast furnace to form a mixture of carbon and nitrogen. Exchanging heat and reacting with the raw materials descend from the furnace top and mixture ascend the furnace. Discharged gas from the top blast furnace is used to preheat the blast. The gas is discharged from the furnace to furnace top and recovered for use as fuel in the works. During the process of charging of different layers of materials, the lower thickness ratio of iron-bearing materials to coke charge from the furnace and their radial distribution are controlled. In this way, the hot blast can pass the appropriate radial distribution. The burden descends into furnace. In the same time, the iron-bearing materials are indirectly reduced by carbon monoxide gas in the low temperature zone on the upper furnace. By the reduction of the remaining iron ore by monoxide, the carbon dioxide is produced. In the lower part of the furnace, it is instantaneously reduced by coke into carbon monoxide. The carbon monoxide reduces the iron oxide. The sequence can be seen as a direct reduction of iron ore by solid carbon in the high temperature zone in the lower furnace. The reduction iron melts, drips, and collects as hot metal in the hearth. The hot metal is molten slag discharged at fixed intervals. The operation is made by opening the top holes and cinder notch in the furnace wall. In the figure, we can see the mushroom, top hole, through, slag runner, skimmer, and iron runner. In the picture, I'll show the tires and deadman lie in the blast furnace. There is a zoom at the hearth, and we can find bird nest, deadman, and mushroom. The blast furnace has a conical shape. It's subdivided into various zones in order to divide the physical and chemical state of the feed materials and products. There are 5 zones of the blast furnace: throat, shaft, in which the ores are heated and reduction reaction starts. Bailey or Bosch parallel. Bosch, the ore reduction completes and the ores are melting down. Hearth, in which the molten material, slag and hot metal, are collected and tapped through the top holes. In the blast furnace, there are other 5 zones. Primary reduction zone, in which the higher valency iron oxides are reduced. Thermal reserve zone, where we have a reduction of austite or metallic iron. Cohesive zone, in which the material starts to soften and melt except the coke particles. Active coke zone, dripping zone, where the final reduction to metallic iron completes, melts with slag and hot metal from drip through the coke layer. And finally, we have deadman. There are pars packed bed of unreacted coke particles sitting or floating on the hearth. Carburization of hot metal. The iron ore feed states in hematite, magnetite, austite, and metallic iron. The reduction process of iron ore particles is process of oxygen removal from the iron oxides. The reduction of iron monoxide is released by CO and H2 gas and by the solid coke particles. CO is generated by coke combustion and the raceway and gasification reaction at a temperature above 1100 degrees centigrade. The metallic iron and CO gas are generated in the hot zone above the raceway by the direct reaction of iron oxide, the coke particle. It takes place into 2 processes: CO reduction to VO, conversion of CO2 to CO in contact with coke. Direct reduction uses carbon as a reductant and generates extra CO gas. It costs a lot of energy. Complete and direct reduction is also called gas reduction. It takes place between CO or H2, the solid burden materials of iron oxides. It removes about 2/3 of total oxygen of iron ore. The indirect reductions are hematite, magnetite, and austite. In the figure, we can see top gas, throat, burden, coke, cohesive zone, active coke zone, deadman, raceway, here, top hole, stack, shaft zone, and belly-Bosch parallel. The combustion energy is used to heat up the burden, and the generated CO gas is used to reduce the iron oxides. Indirect reduction is controlled by temperature and equilibrium CO partial pressure. In the figure, we can see a zone of magnetite, the iron, and wüstite. Coal, oil, and natural gas are used as auxiliary reductant because they permit a lower cost of hot metal. Coal is the most commonly used, and thanks to its low cost, it's possible to lower the coke rate. But also, it allows higher blast temperatures to be used, which also leads to a lower coke rate. Coal injection leads to increased productivity by using oxygen-enriched blast. Coal for injection is categorized by their volatile matter content. Before the coal is injected into the blast furnace, the following steps have to be done. Grinding, in which the coal is grounded to small sizes to enter in the tires, and drying. The most important properties to determine the coal quality are replacement ratio. The amount of coke replaced by the coal depends on the composition and moisture content. Composition, high phosphorus and sulfur content are likely to increase cost in steel plant. Volatile matter, high volatile coal has a low replacement ratio, but it is easily gas-filled in a raceway. Hardness, the size of ground coals is dependent on hardness and equipment designed for it. And finally, we have a moisture content. Sticking and handling problems can be caused by moisture of the coal. Hot metal produced in blast furnace is transferred to a ladled ore or to a vessel called the torpedo car, and then is charged into the basic oxygen steelmaking (BOS). During the oxygen blowing process, the hot metal is decarburized and converted to steel. This process is carried out mostly in the basic oxygen furnace (BOF). Increasingly strength quality requirements have heated and the demand for steels with very low levels of impurities such as phosphorus, sulfur, hydrogen, nitrogen, oxygen, and non-metallic inclusions. High purity cannot be reached by BOS, since its refining capability is limited. Therefore, a method for dividing the refining capability and allocation the divided function to processes before and after the BOS has been put into practical use. The actual process for high-grade steels is an integrated process of smelting in the blast furnace, hot metal pretreatment, decarbonization, and in the BOS, and secondary refining. In the hot metal pretreatment process, the impurities are removed from the hot metal before BOS. The layout of hot metal pretreatment is shown in a figure. We can find slag recycling, desalinization, slag separation, dephosphorization, and slag separation.